Hi guys, the next part of number and algebra that we'll be covering will be binomial theorem. So what's a binomial? Something that looks like this. That's what a binomial is. Alright, so the binomial theorem gives us a way of finding the expansion of a plus b to the power of n. For now, we're just going to go through for when n is a natural number, so like 1, 2, 3, 4. So this formula is in the formula booklet, but even though it is, I advise you guys to try to memorize it, okay? So that you can expand binomials a lot faster. So what does it say? It says that a plus b to the power of n equals to a to the power of n plus n choose 1, a to the power of n minus 1b. Okay, so it looks like a lot of stuff here. But what we can see is that for the powers of a, it goes from the power of n, then n minus 1, n minus 2, and then finally a to the power of 0, which is just 1. Right? But for b, instead it's slightly different. We'll start from b to the power of 0, b to the power of 1, b squared all the way until b to the power of n. So for b, we're just going to increase in power, okay, as the terms go on. While instead, for a, we're going to decrease in power. That's how I remember it, okay? And the next thing, this thing, what is n choose 1? N choose 1 is actually just n. N choose 2 would just be n minus 1 over 2 factorial. And similarly, n choose 3 would just be n minus 1, n minus 2 over 3 factorial. And this pattern continues for any n choose r. We'll be using this a little bit more in permutations and combinations. Alright, but for now, this is all that we need to know to compute the choose function, or also known as the binomial coefficient. Alright? Okay, so now let's do the first question. Find the first 3 terms of the expansion 2 plus x to the power of 5. So what are the first 3 terms? Okay, this will be the first term. This will be the second term. This is the third term, and so on and so forth. So we simply just use the binomial formula. 2 plus x to the power of 5. So we'll do 2 to the power of 5 plus 5 choose 1 of, and then we reduce the power by 1, and then we have x to the power of 1. And then we have 5 choose 2, and we reduce the power of 1 again, and increase the power of 1 for x. Okay, so we have x squared, and then we plus dot dot dot. And if we evaluate this correctly, we should get 32 plus 80x plus 80x squared. And that's the first 3 terms of your expansion. Alright, let's do another question. Find the term independent of x in the expansion of this thing. Okay, first of all, what is the term independent of x? If you think about it, the term independent of x is just the constant term. Okay, so I've neglected to tell you one thing. The general term tr plus 1 equals to n choose r times a to the power of n minus r times b to the power of r. Alright, so let's use this to find the term independent of x in this expansion. We'll use the general term because we don't want to expand out all the terms just to find out what one term is, right? So let's write down tr plus 1 equals to n, which is 15, choose r. Okay, in this case, we don't know what r is yet, times a, which is 2x, to the power of n minus r times b to the power of r. Okay, let's simplify this a little. Okay, so we will have 2 to the power of 15 minus r times x to the power of 15 minus r times negative 1 to the power of r times 2 to the power of negative r, because half the power of r is actually just 2 to the power of negative r, and then x to the power of negative 2r. And simplifying this, okay, let's combine the 2's together. We'll get 2 to the power of 15 minus 2r times negative 1 to the power of r times x to the power of 15 minus 3r. And here, this is where we find out what r is. So we want the term independent of x, which means 15 minus 3r equals to 0. If not, x will have a power, and that would not be the term independent of x. So if we equate it to 0, we realize that r equals to 5. And let's just sub it in. So if we sub in r equals to 5 into this over here, what we get is, the term is negative 96096. Alright? So that's it for the binomial theorem for natural numbers.